Welcome back. Today we will discuss differentiation of vector valued functions. The theory of vector valued functions is same as that of real valued functions, so that we can discuss limit, continuity and differentiation of vector valued functions. We begin with the definition of vector valued functions. Vector valued functions. A vector valued function r is equal to r of t is a rule that associates a vector r of t with each real number t in some set, usually an interval a less than or equal to t less than or equal to b, or a collection of intervals. In other words, a vector valued function is a function of the parameter t that produces a vector. Noting that I, j, k be a right-handed triad of mutually perpendicular non-coplanar unit vectors, usually we denote a vector valued function r is equal to r of t by r is equal to r of t is equal to xti plus ytj plus ztk, put it as equation 1, where xt, yt and zt are real valued functions of the variable t. As t increases from its initial value t0 to the value t1, the point xt, yt, zt trace out some geometric object in space. It may be straight line or curve. This geometric object is called space curve or arc. An example of a vector valued function is r is equal to r of t is equal to 1 by ti and is defined for minus infinity less than t less than 0 and 0 less than t less than infinity. The function is not defined at t is equal to 0. Limits of vector valued functions. The way we define limits of vector valued functions is similar to the way we define limits of real valued functions. Definition. Let Rt is equal to Fti plus Gtj plus Htk be a vector valued function and L be a vector. We say that R has limit L as t approaches t0 and write limit t tends to t0 Rt is equal to L if for every number epsilon greater than 0, there exists a corresponding number delta greater than 0 such that for all t, 0 less than mod t minus t0 less than delta implies mod Rt minus L less than epsilon. If L is equal to L1i plus L2j plus L3k, then limit t tends to t0 Rt is equal to L when precisely limit t tends to t0 f of t is equal to L1, limit t tends to t0 g of t is equal to L2 and limit t tends to t0 h of t is equal to L3. The equation limit t tends to t0 Rt is equal to limit t tends to t0 f of t into I plus limit t tends to t0 g of t into j plus limit t tends to t0 h of t into k provides a practical way to calculate limits of vector functions. Remarks. Limit t tends to t0 Rt is equal to L means that the magnitude of Rt is approximately the magnitude of L and that if L is non-zero, the angle between them is approaching 0. See figure 1. Equivalently, the components of R of t are approaching the components of L. The definition just given is identical to that provided in calculus books for real valued functions, except that the expression mod Rt minus L now refers to the magnitude of the vector rather than to the absolute value of a number. Continuity of vector valued functions. Definition. A vector function Rt is continuous at a point t is equal to t0 in its domain if limit t tends to t0 Rt is equal to Rt0. The function is continuous if it is continuous at every point in its domain. Component test for continuity at a point. Since limits can be expressed in terms of components, we can test vector functions for continuity by examining their components. The vector function Rt is equal to Fti plus Gtj plus Htk is continuous at t is equal to t0 if and only if the component functions f, g and h are continuous at t0. Before we give an example, we first familiar with the floor function. The function whose value at any number x is the greatest integer less than or equal to x is called the greatest integer function or the integer floor function. It is denoted by the greatest integer x. observe that the greatest integer of 2.9 is equal to 2, the greatest integer of 1.2 is equal to 1, the greatest integer of 0 is equal to 0, the greatest integer of minus 3.2 is equal to minus 4. Example, the function g of t is equal to cos t I plus sin t j plus the greatest integer t into k is discontinuous at every integer. We note that the components cos t and sin t are continuous everywhere, but the integer floor function box t is discontinuous at every integer. Hence, g of t is discontinuous at every integer. Derivatives. Definition. A vector function Rt is said to be differentiable at t naught if the limit delta t tends to 0 r of t naught plus delta t minus r of t naught divided by delta t exists, and then the limit is called the derivative of r of t at t naught and is written as r dash t naught or d by dt of r of t naught or dr by dt at t is equal to t naught. If Rt is differentiable at every point t for which it is defined, we simply say that Rt is differentiable. Derivative of vector valued function in terms of components. Let Rt is equal to Fti plus Gtj plus Htk, where f, g and h are differentiable scalar valued functions of t. Then dr by dt is equal to limit delta t tends to 0 r of t plus delta t minus r of t divided by delta t is equal to limit delta t tends to 0 f of t plus delta t minus f of t divided by delta t into I plus limit delta t tends to 0 g of t plus delta t minus g of t divided by delta t into j plus limit delta t tends to 0 h of t plus delta t minus h of t by delta t into k is equal to df by dt into I plus dg by dt into j plus dh by dt into k. Definition. The curve traced by r is smooth if dr by dt is continuous and never 0. Definition. If r is the position vector of a particle moving along a smooth curve in space, then Vt is equal to dr by dt is the particle's velocity vector and is tangent to the curve. At any time t, the direction of v is the direction of motion, the magnitude of v is the particle's speed, and the derivative a is equal to dv by dt when it exists is the particle's acceleration vector. Theorem 1. If u and v are differentiable vector functions of t, then scalar multiple rules. D by dt of c into u is equal to c into du by dt for any scalar number c. D by dt of f into u is equal to df by dt into u plus f into du by dt for any differentiable scalar function f of t. Sum rule. D by dt of u plus v is equal to du by dt plus dv by dt. Difference rule. D by dt of u minus v is equal to du by dt minus dv by dt. Dot product rule. D by dt of u dot v is equal to du by dt dot v plus u dot dv by dt. Cross product rule. D by dt of u cross v is equal to du by dt cross v plus u cross dv by dt. Chain rule. Short form. If r is a differentiable vector function of t and t is a differentiable scalar function of s, then dr by ds is equal to dr by dt into dt by ds. Proof of the dot product rule. Suppose that u is equal to u1ti plus u2tj plus u3tk and v is equal to v1ti plus v2tj plus v3tk. Then d by dt of u dot v is equal to d by dt of u1v1 plus u2v2 plus u3v3 is equal to u1 dash v1 plus u2 dash v2 plus u3 dash v3 plus u1 v1 dash plus u2 v2 dash plus u3 v3 dash is equal to du by dt dot v plus u dot dv by dt. Proof of the cross product rule. According to the definition of derivative, d by dt of u cross v is equal to limit h tends to 0 u of t plus h cross v of t plus h minus u of t cross v of t divided by h. To change this fraction into an equivalent one that contains difference quotients for the derivatives of u and v, we subtract and add u of t cross v of t plus h in the numerator. Then d by dt of u cross v is equal to limit h tends to 0 u of t plus h cross v of t plus h minus u of t cross v of t plus h plus u of t cross v of t plus h minus u of t cross v of t divided by h is equal to limit h tends to 0 u of t plus h minus u of t divided by h cross v of t plus h plus u of t cross v of t plus h minus v of t divided by h is equal to limit h tends to 0 u of t plus h minus u of t by h cross limit h tends to 0 v of t plus h plus limit h tends to 0 u of t cross limit h tends to 0 v of t plus h minus v of t divided by h. The last of these equalities holds because the limit of the cross product of two vector functions is the cross product of their limits if the latter exists. As h approaches 0, v of t plus h approaches v of t because v being differentiable at t is continuous at t. The two fractions approach the values du by dt and dv by dt at t. In short, d by dt of u cross v is equal to du by dt cross v plus u cross dv by dt. Proof of the chain rule. Suppose that RT is equal to FTI plus GTJ plus HTK is a differentiable vector function of t and that t is a differentiable scalar function of some other variable s. Then f, g and h are differentiable functions of s. The chain rule for differentiable real valued functions gives dr by ds is equal to df by ds into I plus dg by dt into j plus dh by dt into k is equal to df by dt into dt by ds into I plus dg by dt into dt by ds into j plus dh by dt into dt by ds into k is equal to df by dt into I plus dg by dt into j plus dh by dt into k into dt by ds is equal to dr by dt into dt by ds. The other results follow immediately from the definitions. Example 1. Show that r dot dr by dt is equal to r into dr by dt, where r is equal to mod vector r is equal to root of x square plus y square plus z square. Solution. Let r is equal to xti plus ytj plus ztk. Then dr by dt is equal to dx by dt into I plus dy by dt into j plus dz by dt into k, and small r is equal to square root of x square plus y square plus z square. Vector r dot dr by dt is equal to xi plus yj plus zk dot dx by dt I plus dy by dt j plus dz by dt k is equal to x into dx by dt plus y into dy by dt plus z into dz by dt. Also, dr by dt is equal to 1 by 2 into square root of x square plus y square plus z square into 2x dx by dt plus 2y dy by dt plus 2z dz by dt, or dr by dt is equal to x into dx by dt plus y into dy by dt plus z into dz by dt divided by square root of x square plus y square plus z square is equal to r dot dr by dt divided by r. Hence, vector r dot dr by dt is equal to r into dr by dt. Constant vectors. A vector changes if either its magnitude changes or its direction changes or both direction and magnitude changes. Hence, a vector is constant when both its magnitude and direction are fixed. Theorem 2. The necessary and sufficient condition for the vector function f of t to be constant is that df by dt is equal to 0, the 0 vector. Proof. Necessary part. If f of t is constant, then f of t plus delta t is equal to f of t. Hence, df by dt is equal to limit delta t tends to 0 f of t plus delta t minus f of t divided by delta t is equal to limit delta t tends to 0 f of t minus f of t divided by delta t is equal to 0. Sufficient part. Suppose that df by dt is equal to 0. Let f of t is equal to f1t I plus f2t j plus f3t k. Then df by dt is equal to df1 by dt into I plus df2 by dt into j plus df3 by dt into k. Hence, using the assumption df by dt is equal to 0, we have df1 by dt into I plus df2 by dt into j plus df3 by dt into k is equal to 0i plus 0j plus 0k. Equating the coefficients, we get df1 by dt is equal to 0, df2 by dt is equal to 0, df3 by dt is equal to 0. This shows that f1, f2 and f3 are constants and hence they are independent of t. Therefore, f of t is a constant vector. Theorem 3. The necessary and sufficient condition for the vector function f of t to have constant magnitude is that f dot df by dt is equal to 0. Proof. Let f be a vector valued function of the scalar variable t. Suppose that f of t has constant magnitude, say f, so that mod f is equal to f, a constant. Then f dot f is equal to f square, a constant. Therefore, d by dt of f dot f is equal to 0 or f dot df by dt plus df by dt dot f is equal to 0 or 2f dot df by dt is equal to 0 or f dot df by dt is equal to 0. Conversely, suppose that f dot df by dt is equal to 0, then 2f dot df by dt is equal to 0 or f dot df by dt plus df by dt dot f is equal to 0 or d by dt of f dot f is equal to 0 or d f square by dt is equal to 0. And this shows that f square is a constant and hence f is a constant. That is, the vector function f of t have constant magnitude. Theorem 4. The necessary and sufficient condition for the vector function f of t to have constant direction is that f cross df by dt is equal to 0. Proof. Let f of t be a vector function of the scalar variable t and n be a unit vector in the direction of f of t. If f be the magnitude of vector f, then f is equal to fn. Hence, f cross df by dt is equal to fn cross d by dt of fn is equal to fn cross f into dn by dt plus df by dt into n. Since d by dt of fn is equal to f into dn by dt plus df by dt into n is equal to f square into n cross dn by dt plus f into df by dt of n cross n is equal to f square into n cross dn by dt. Since n cross n is equal to 0, put it as equation 1. Necessary part. Suppose that f has constant direction, then n is a constant vector. Therefore, dn by dt is equal to 0. Hence, from 1 above, we have f cross df by dt is equal to 0. Sufficient part. Suppose that f cross df by dt is equal to 0. Then from equation 1, we get f square into n cross dn by dt is equal to 0 or n cross dn by dt is equal to 0. Put it as equation 2. Since n is of constant length, by the last theorem we have n dot dn by dt is equal to 0. Put it as equation 3. From equations 2 and 3, we obtain dn by dt is equal to 0. Hence, n is a constant vector. Therefore, the direction of f is constant. Definition. The scalar triple product or box product of three vectors a, b and c denoted by box ABC is defined as box ABC is equal to a dot b cross c. Example. Show that d by dt of box UVW is equal to box du by dt VW plus box u dv by dt W plus box uv dw by dt. Solution. d by dt of box UVW is equal to d by dt of u dot v cross w is equal to u dot d by dt of v cross w plus du by dt dot v cross w is equal to u dot v cross dw by dt plus dv by dt cross w plus du by dt dot v cross w is equal to u dot v cross dw by dt plus u dot dv by dt cross w plus du by dt dot v cross w is equal to box u v dw by dt plus box u dv by dt w plus box du by dt v w is equal to box du by dt v w plus box u dv by dt w plus box u v dw by dt. Example, show that d by dt of u cross v cross w is equal to du by dt cross v cross w plus u cross dv by dt cross w plus u cross v cross dw by dt. Solution, d by dt of u cross v cross w is equal to u cross d by dt of v cross w plus du by dt cross v cross w using theorem 1 cross product rule is equal to u cross dv by dt cross w plus v cross dw by dt plus du by dt cross v cross w is equal to u cross dv by dt cross w plus u cross v cross dw by dt plus du by dt cross v cross w is equal to du by dt cross v cross w plus u cross dv by dt cross w plus u cross v cross dw by dt. Example, show that ut is equal to sin t I plus cos t j plus root 3 k has constant length and is orthogonal to its derivative. Solution, ut is equal to sin t I plus cos t j plus root 3 k and mod ut is equal to square root of sin t the whole square plus cos t the whole square plus root 3 whole square is equal to square root of 1 plus 3 is equal to 2. Also, du by dt is equal to cos t I minus sin t j and u dot du by dt is equal to sin t cos t minus sin t cos t is equal to 0. Successive derivatives. If r is a vector function of the scalar variable t, then d by dt of r is also in general a vector function of t. So, if dr by dt is differentiable, its derivative d by dt of dr by dt is denoted by d square r by dt square and is known as the second order derivative of r. Similarly, the derivative of d square r by dt square is denoted by d cube r by dt cube and is called the third order derivative of r, and so on. The derivatives dr by dt, d square r by dt square, d cube r by dt cube are also represented by r dot, r double dot, r dot dot dot. Example, prove that f cross d square g by dt square minus d square f by dt square cross g is equal to d by dt of f cross dg by dt minus df by dt cross g. Solution, d by dt of f cross dg by dt minus df by dt cross g is equal to d by dt of f cross dg by dt minus d by dt of df by dt cross g is equal to f cross d square g by dt square plus df by dt cross dg by dt minus df by dt cross dg by dt plus d square f by dt square cross g is equal to f cross d square g by dt square minus d square f by dt square cross g. Example, if f is a vector function of the scalar variable t, show that d by dt of box f f dash f double dash is equal to box f f dash f triple dash. Solution, d by dt of box f f dash f double dash is equal to d by dt of f dot f dash cross f double dash is equal to df by dt dot f dash cross f double dash plus f dot d by dt of f dash cross f double dash is equal to f dash dot f dash cross f double dash plus f dot f dash cross df double dash by dt plus df dash by dt cross f double dash is equal to f dot f dash cross f triple dash plus f dot f double dash cross f double dash is equal to f dot f dash cross f triple dash plus 0 is equal to f dot f dash cross f triple dash. Partial derivatives of vector valued functions. Suppose f is a vector depending on more than one scalar variable, say x, y and z, that is f is equal to f of x, y, z. Then the derivative, if it exists, of f with respect to x keeping other variables as constants is called the partial derivative of f with respect to x and is denoted by dou f by dou x. That is, dou f by dou x is equal to limit delta x tends to 0 f of x plus delta x y z minus f of x y z by delta x provided this limit exists. Similarly, dou f by dou y is equal to limit delta y tends to 0 f of x y plus delta y z minus f of x y z by delta y. Dou f by dou z is equal to limit delta z tends to 0 f of x y z plus delta z minus f of x y z by delta z are the partial derivatives of f with respect to y and z respectively, provided these limits exist. For functions of two or more variables, we use the term differentiable to mean that the function has continuous first partial derivatives. Higher derivatives can be defined as follows. Dou square f by dou x square is equal to dou by dou x of dou f by dou x. Dou square f by dou y square is equal to dou by dou y of dou f by dou y. Dou square f by dou z square is equal to dou by dou z of dou f by dou z. Dou square f by dou x dou y is equal to dou by dou x of dou f by dou y, etc. Theorem 5. If f and g are functions of x, y, z, then a. Dou by dou x of f plus g is equal to dou f by dou x plus dou g by dou x. b. Dou by dou x of f dot g is equal to dou f by dou x dot g plus f dot dou g by dou x. c. Dou by dou x of f cross g is equal to dou f by dou x cross g plus f cross dou g by dou x. Now, let us summarize what we have discussed today. There is a close similarity between the calculus of scalars and calculus of vectors as regards limits, continuity and differentiability of vector functions of scalar variables. These concepts of vector valued functions are defined using the respective property of scalar functions. In this unit, the differentiation rules and derivative of vector valued functions in terms of scalar component functions are discussed with the help of examples. Important theorems stating the necessary and sufficient conditions for a vector valued function to have constant direction and constant magnitude are proved. The results of successive derivatives are also included. Before we attend the next unit, please try to answer the following questions. 1. If Rt is equal to cos t I plus sin t j plus t k, find limit t tends to 0 Rt and limit t tends to pi by 4 Rt. 2. The vector Rt is equal to 6 cos t I plus 6 sin t j plus t cube k gives the position of a moving body at time t. Find the body's speed and acceleration when t is equal to 1. At times, if any, are the body's velocity and acceleration orthogonal. 3. A particle moves along the curve x is equal to 3t square, y is equal to t square minus 2t, z is equal to t cube. Find the velocity and acceleration at t is equal to 1. 4. Show that if b, c, d are constant vectors, then Rt is equal to bt square plus ct plus d is a path of a point moving with constant acceleration.